Hey there, everyone. Hope you're all well. So today I'm going to continue with the series I'm on. This is about machine learning for environmental protection, and today the focus is going to be on improving recycling initiatives, and we're going to use Python, of course. All the teaching lessons that I put out here have Python, virtually all. There's a couple exceptions, but not too many. So we're going to use machine learning to help us understand environmental protection and figure out how we can run this process better, right? Or manage the process better. And machine learning can definitely help us in many respects. There's a few shortcomings, and we'll see those in just a minute. I'm going to show you what to do. And then I actually ran some experiments. I was hopeful and anticipating that they would turn out well, but they actually didn't. But I'll take you through those anyways, just to show you that machine learning is not a solution for every single problem in the world, right? You have to apply the right algorithms, and you have to have the right data set too. If you have the wrong data set and you're using the wrong algos, you're really going to just be spinning your wheels. So I'll just show you a couple examples of that, but we'll focus on the successes and diminish the failures here. So machine learning basically is great in many types of applications, certainly recycling, environmental protection. This is just the tip of it, though. There's so many things you can do. In all my videos, you can see lots of different applications for machine learning initiatives, right? So in this case, we're going to look at urban planning and urban energy planning, focusing mostly on recyclables, renewable energy integration, industrial process optimization. We view that just a little bit, not too much in this video, but in the series, I'm doing a bunch of videos about environmental protection. We're going to look at transportation optimization. That was actually one of the last videos I did. That kind of overlaps a little bit in this one. And building energy efficiency, we're going to take a look at that too. So I created this synthetic data set. Now, I'll admit I couldn't find what I was looking for online. I did some searching. After a while, I gave up and just created my own data set because I think this illustrates the point very nicely. I looked for the data that I really wanted to present to you. I couldn't find it. So again, I just made up my own data. Okay, so that's what this is for. We have a few different features: city size, public transportation usage, renewable energy usage, average temperature, outside per capita income. This is income per head count. Okay, so income per person. You would take the total income of your whatever you're looking at. In this case, it's different sizes of cities, and divide by the population size. So the per capita income is a nice way to adjust the expenditures or the expenses for your city based on the population of the city. Okay, and we're going to package that very nicely into a data frame. Okay, you can see the data frame right here. Now, I'm not going to actually run this cell. I could, some below I actually can't because I need a Google API key, so Google Maps key, or a Google, what's it called? Google Directions, I think, key. So I can show you how to get that. Let's see, Google Maps API key, Google API key. Now, this is 100% free. It's very fast and easy to set up and get this process running on your computer. I can't share my key with you for obvious reasons. This is confidential and personal and very classified. So everybody that gets their own key, you should get that directly from Google. Don't share keys. Don't accidentally drop your key or give it out in code or something like that. This is all personal to your account and your setup. So you want to protect your Google key and not disclose that to anybody else. Okay, so you can see I did a quick Google search here, and I got to my Google Cloud platform, or GCP. So that is just literally Google Maps API key, and then you click on here, Google Cloud Platform. Okay, so simple Google search will take you there. You have to create the key. You would want an API service, and there's a bunch of services here. Probably by now there's close to 100, give or take. You can see all the service names on the side. So a lot of these are cloud, Firebase hosting, places, secret manager. Let's look for maps. If I do Control F, maps, MAPS. And I'm not seeing that. Google Places maybe would be a suitable key. And I think there's Google Directions. Let me see if I can find Directions. DIREC. No, they don't have that. So maybe everything is consolidated into, what is this? Google Places now? That might be it. I thought they used to have 3 different ones. I did have a couple different API keys. There's air quality pollution, Google Maps Street View, maybe this is it. Let me see real quick. PS, Google Maps. Okay, so I think they do have a couple. So anyways, the point is you would go over here and create your own key. Just follow the instructions. It's very quick and easy to do that. If I click this off and click that off, time zone, roots API, geocoding API. So there's a whole bunch of them. Okay, so you would just pick the one that's relevant to you. You can pick, actually, I think there's overlap here, either Google Streets or Google Maps or Google Places. I think all three of those would work for you. So just go there, set yours up. Mine is already set up. So I would put that in here. When you go ahead and set this up on your system, you would put your key right here, and all the other code is going to remain exactly the same. So I'm giving you this data sample. Again, I created this. I couldn't find it online, so I created it myself. Then I put in a handful of addresses. It looks like 5 addresses here. So I'm just going to start with 5. You can put in 50, you can put in 500, 5,000. It doesn't matter. The algorithm is going to run over everything in this list. You can tell this is a list by the square brackets, right? We have an open square bracket, a closed square bracket. Dictionary is going to have curly braces with key value pairs, and a tuple is going to look kind of like a list, but it's going to have curly brackets, right? So we can tell this is a list. You'll loop through all the items in the list and pull back the optimized direction for this vehicle. This is going to be a recycle vehicle that leaves from this address, the recycling center, goes to all of these addresses, but not in a specific order. It's going to go to all the addresses in the most efficient order to minimize the time that it spends driving around picking up recyclable items. And when you minimize the time, you minimize the distance traveled. So you save time, you save gas. It's a win-win scenario, okay? So I think in this situation, we are actually going through these 5 addresses randomly in no particular order. If I scroll down just a little bit, you can see we're looping through the list. This is collection address. If I do Control F, you can see collection address there, and I think we'll see that one or two other times. Recycling center plus address. Okay, so here's the setup, right? We're going to start at the recycling center, go to all the addresses, and then go back to the recycling center just to make sure it's apples to apples comparison. So if we start at any one point randomly and finish at any one point randomly, that may or may not be the optimized route. We want to start at this recycle center. This is Boulder, Colorado. Okay, so if I zoom in, you'll see Boulder Recycling Center. So that is the origin and the destination. If I zoom out on the map, you can see the vehicle follows the roads here. Okay, it doesn't just go straight. If we went in a straight line from the recycle center to the first address here, if I click on it, it looks like 100 Pine Street. That would be the shortest distance. What you all learned in school, in primary school, the shortest distance between 2 points is a straight line, right? Shortest distance between 2 points is a straight line. But you're not flying, you're driving. So you have to follow the contours of the streets. So it's kind of an impediment or a restriction. You have to follow the contours of the streets. But even when we follow the contours of the streets, we can still pick up all the recycled items just going in a minimum distance as minimized and as optimized as we can make it without backtracking or going out of the way, right? We're going to go pick up all these recyclable items, start at the recycle center, do the task, pick up all the items, and return to the recycle center. And we're going to compare 2 scenarios where this is done randomly, okay, and where this is done in an optimized fashion. And I just picked Boulder, Colorado, because I like this place. I've been here a couple of times. I really like the environment. It's very outdoorsy, fresh air, lots of hiking, biking, outdoors activities, things like that, swimming and kayaking and all kinds of stuff. So I like Boulder, that's why I picked this. So we have 5 addresses here. We're going to start at the recycle center, go to these 5 in just one random order, not particularly picking any one address over the other. And every time you run this, you'll see the sequence of addresses are displayed differently. Okay, so I'm not going to run this because I'm not going to share my API key, and that will fail if I refresh this view. But the last time I ran this, you can see these are the addresses it picked up. So it started at the recycle center. The total distance traveled is 18,008 meters, and it went to all these addresses. So 1901, 63rd, 1111, Canyon, 1010, Walnut, 456, 79, 10 Pine Street, 100 Pine Street, and 1901, 63rd Street. Okay, so we go to all the addresses. We start at the recycle center and end at the recycle center. The vehicle travels 18,008 meters. So that is a non-optimized random address pickup. Now, if we optimize the scenario of picking up these recyclable items, right, from all the recycled containers that people leave in front of their house, we can actually use an optimization process and solve this so the total distance traveled is minimized. And we can see that right here, 16,928 meters is the optimized route. And we save 1,080 meters over the arbitrary randomized route. Okay, so if we go over here, this is kind of random. It's not any particular order. And we have 6 stops, 1, 2, 3, 4, 5. I'm sorry, 5 stops. We have 5 stops. We go to all the stops. This is not the optimized way to do it. This is the optimized way to do it. We start with the recycle center, go to these stops, and then go back to the recycle center. So instead of making a big loop, you can actually see we go to this site, and then this one, and then this one. Come back over here, go to this guy, and go back, and it's only 16,928 meters. If we go actually in a loop, it kind of looks like it's more efficient. I guess because this route goes out of the way, this top blue line is out of the way, it's actually further distance, and obviously the more you drive, the longer it's going to take, and the more gas you're going to burn too. So this is the non-optimized solution, 18,008 meters if you go in this order, right? And this is the optimized solution. And we got, what is this, 16,928 meters. So you save time, save gas, and save resources, wear and tear in the vehicle, and so on and so forth. So that is the optimized route. So there we use machine learning and an optimization routine to improve how recycling is done in the city of Boulder. And again, this is just 5 addresses. You can put in 50 or 5,000, it doesn't matter. The algo is going to rip through all those pretty fast and pretty efficient and show you the optimal route to follow. Okay, so go ahead and try that, add in more addresses at your leisure, or go ahead and set this up for your own neighborhood, your own local neighborhood, add in the addresses here. You would want to add a start and end point. This is the recycle center. That's the only thing you're going to have to change. You would change these variables and nothing else. And add your API key, of course, right? You'll get that over here from Google API Services, and you are good to go, right? So that's how you optimize the distance between different pickup points and drop-off points and so on and so forth. This is called the traveling salesman problem, abbreviated TSP, traveling salesman problem, and you want to go to all the points that you need to go to and do it in the optimized time and optimized distance traveled, right? So shortest time, shortest distance. That's the TSP problem. And I have a few other videos on my channel where I solve that, so you can keep an eye out for that if you're interested in learning more about it. So in this example, I want to do some clustering, and I'm going to look at these features right here. So these are the independent features. I'm putting this into a variable called features, and this comes from this data frame. I have population density, average household size, industrial activity level. If we go back to the data frame, you'll see all of those over here. So this is the original data frame: city size, population density, average household size, public transit, industrial level, renewable energy usage, that's important, average temperature in centigrade, per capita income, that's the income spent, divided by all the households or by the population, right? Energy consumption, emissions, recycling, waste generated, recycling bin, accessibility, and public awareness score. So this is the public awareness campaigns about recycling. That's what that number is, right? So we saw the optimization. That was pretty useful. That was successfully executed and validated right here. Let's look at another example using machine learning. We're going to look at clusters of, what are we looking at? Basically all of these features. We're going to try to cluster all these together. So the most similar features are the most homogeneous, and these are going to be clustered in the same cluster. And if they're different and more heterogeneous, they are pushed into different clusters. And we have a total of between 1 and 11 clusters. We're doing an elbow curve here to help us determine how many clusters are the optimal cluster. And the elbow curve takes your elbow and kind of bends it. If you can imagine your left or right arm bending, the elbow part is kind of the biggest bend in the curve, so it kind of looks like an elbow, or so they say. I guess that's how this got its name. It's kind of a funny name, but I guess it kind of makes sense. So the biggest bend would be the optimal number of clusters, and you have depreciating returns after the biggest bend, right? So it looks like it's about 2 or 3, maybe you can argue 4, definitely by 5. The curve is flattening out, so I would say it's about 3 or 4. I think I picked 3 over here for clusters. Oh, actually 2. Okay, so I ran this a couple times. I said the cluster bend is biggest at 2. You could say 2 or 3. I think either one you can make an argument for. And then based on these features over here from our data frame, population density, average household size, industrial activity, recycling, and so on and so forth, public awareness score. We're taking all these features and clustering them together, right, to see how everything shakes out. I'm saying there's going to be 2 different clusters right here, and the 2 comes from, where'd it go? Oh yeah, right here, clusters equal 2. And we're going to start randomly, right, with a clustering algorithm. You start at a random point, and the clustering algo moves around, pulling and pushing different data points into the cluster or pushing them away, right, depending on the approximate distance between the cluster centers, right? So I've got a couple videos in this. You look at the centroid or the center of the cluster and measure the distance. It's like an XY distance, the X being the horizontal, the Y being the vertical. Measure the distance between those. If they're shorter, they go into the same cluster. If they're longer, they go into different clusters. So that is how that works. And I've got several videos about clustering. You can check those out. So we go ahead and take everything and put that into this data frame that we just created. We append one new field onto the existing data frame. It's called DF cluster. So you can see the original data frames here. Public awareness, recycling bins. Here's cluster. That's where we get the cluster number, 0 or 1. We have the optimal recycling strategy. And then is this an anomaly or is this normal? And we'll get to that in just a minute. We actually haven't run those algorithms yet. We're up to this part, but I push everything in the same data frame. So I have data frame name, just abbreviated DF, pretty straightforward. Waste generated per capita by kilograms per year, and then the recycling rate percentage. So if you look over here, waste generated per kilogram. Okay, so for larger neighborhoods, we should see more. This is medium, this is large. So these two are pretty similar in terms of the waste produced, but the medium city should be a little bit longer, a little bit smaller. This is a little bit smaller down here, and this city actually is a medium-sized city, but they have less waste. This is a small city, but they have a lot of waste. Okay, so that's something that probably needs to be addressed at some point. And we're looking at the recycling rate as well, and the recycling rate comes from over here. So this is 18%, 43. Those guys are doing good. This is deplorable over here. It's only 10, so pretty minimal recycling rate. We should work on that. That needs some attention too. So anyways, let's go ahead and create the cluster and plot the results. We can see cluster 0 is in blue, cluster 1 is in yellow. We only had 2 clusters. Remember, we defined 2 over here because of the bend in the curve. We said the biggest bend is 2. You could say maybe 3, maybe even 4, probably 2 or 3 though. So here's the clusters. And I show you this. I don't think this is a huge win. I don't think there's any tremendously useful information because the clusters are just placed all over, right? If you had a certain concentration, like all the yellows are on the left, all the blues are on the right, then I would definitely say clustering is working. Or if the clusters were in the northwest or southeast or isolated in the northeast or southwest, those are working. If you have different colors on the top and on the bottom, those are working. Everything is kind of blended together. So this experiment is kind of wasted. So I told you before, not every single data science experiment is useful. Some are more useful than others. Some are very useful. Some are not so useful. This is kind of a waste. But I just wanted to show you, just to let you know that data science doesn't solve every single problem in the universe. And sometimes you run experiments and the outcome is not really what you expect, right? It doesn't match your hypothesis. So you just kill the experiment, or you don't engage it, or you don't pursue this experiment any further. If you're getting better and better results, you can do it. This is basically pretty massive failure. I'm not seeing any deviation clusters. They're kind of blended together, and there's nothing that's really jumping off the page. So this is kind of a waste of time, but it's still worthwhile to try the exercise and see what the outcome is. I'm just not going to pursue this anymore. This is kind of a dead end, okay? And this is a 3-dimensional view of the same thing. If I zoom in a little bit here, whoops, let me scroll down. If I zoom in a little bit, you can see the details. We can see all the clusters. I love these plotly graphs because they're very interactive. You can actually zoom in and zoom out and spin this around in different dimensions. But again, is this very useful? I don't think so. If you had a lot of blue dots on the bottom or on the top, on the left or the right, yes, it's clustering well. There's delineation between the different clusters. Here, everything is merged together. So here's another experiment, very similar to the one above, just in the 3-dimensional layout. It's not really useful. It's not really helping us, so we're not going to pursue this anymore, okay? The first experiment that we ran here with optimization was very useful, okay? We got 16,928 meters. That's the optimal route. This is a suboptimal route over here. If you look at this, 18,008 meters. We drive further, we burn more gas, and it takes more time. So that is not recommended. This is definitely recommended, this route right here. So that experiment was successful. these clustering exercises were not successful, and that's fine, right? We try it and we see what the outcome is, and then if it's proving to be successful, we pursue it more, and if it's not successful, we do an about face and do a 180 and go in a different direction. So let's look at an experiment using what is this called? Actually, I forgot. Random forest regressor defined. Oh, feature importance. Yes. So this is feature importance. This shows us which features from the independent variables over here in their data frame have the most statistical impact on recycling rate. Okay, so I want to see in the first experiment, I said, what's the optimal route to follow for the vehicle to pick up all the recycled materials and not drive excessively, right? You drive the minimum distance and you fulfill the task of picking up all the recycled materials. That was successful. Now we want to see if we look at the feature importances, which feature importances of these independent variables have a high statistical impact on this feature right here, the recycling rate percent. So is population density going to have a big impact on recycling rate? I don't know, but when we run the experiment, we'll see. How about average household size, industrial activity level, recycling bin accessibility and coded? That sounds like it would be directly linked to this recycling rate. Waste generated per capita, kilograms per year, and public awareness score. That seems like that would be related too. So when we run the experiment, we see waste generated per capita, kilograms per year. That's the metric that we measure in kilograms of waste. And this actually has the most influence on the recycling rate. So the more waste that you generate, the more people try to recycle to diminish the waste, right, or reduce the waste that they generate. Population density has some impact on recycling. Public awareness score, that makes sense to me, that has some impact on recycling. The more public awareness campaigns that you run about recycling, the more people will be aware of that campaign. Average household size, that makes sense. Industrial activity has about 10% influence on recycling rate, and recycling bin accessibility and coded actually has about just over 5, maybe 6% probably impact on the recycling rate percent, but it's actually mostly coming from waste generated per capita. So the more waste you generate, the more people recycle to cut down on the waste. And then the more the population density, the more the recycling. That makes sense to me too. If you have a big population, by and large, more people will be recycling. If you have a tiny population, maybe it's the same relative rate, but probably it's just going to be a handful of people. If you live in a tiny town, it's just going to be a handful of people, but it could still be 50% of the households recycling, right? Maybe it's just 10 houses in a town of 20 people. So it's still the same relative amount, but just by numbers, it's far smaller than a large town, okay? So let us look at this opportunity to reinforce learning and optimize recycling strategies. So reinforcement learning is kind of like where you pay an agent or some type of learning agent, it's called, to undertake a certain behavior, and you encourage it by reinforcing the learning or the outcome of that agent. So if you're playing a chess game against a computer, the computer wants to win chess, right? It's rewarded by saying, congratulations, you won the game, or praises, you did a good job, you achieved success, you beat your opponent. So the reinforcement learning in a chess game will be the computer getting praises or positive input from the programmer saying you're doing a good job, keep it up, right? That's a classic example of reinforcement learning. I want to use reinforcement learning to help us improve our recycling strategies for this town in Boulder, Colorado. So we have a bunch of states we're going to put into a variable. This comes from a data frame: waste generated per capita, population density, public awareness, average household size, industrial activity level, and recycling accessibility. So if you make recycling accessible to people, they're more likely to engage in recycling. If you make it very difficult, they're probably not going to bend over backwards and go ahead and undertake recycling tasks. Hopefully they will, but the easier you make it for people to do that, the more they're going to get on board with that, right? So this is reinforcement learning agent that I set up, and I'm going to give you all the code. You don't have to worry about all the details here, but basically these are the features we're feeding into this variable right here. Okay, if I do Control F, you can see the length of the states is going to iterate through each item in states. These are all the items, right? 1, 2, 3, 4, 5, 6. We have 6 items. So the length is 6, and actions. So these are the positive actions that we can associate with these different features. So again, the features come from the data frame. The actions are add recycle bins, public awareness campaign. So it's some type of marketing. channel, and then increase collection frequently. These are the three tasks that we came up with, or that I came up with, whatever, that say we can try to improve the recycling efforts for the town of Boulder by either doing three things: adding bins, advertising, marketing, same thing, right? Or increase collection frequency. Instead of doing it, whatever, once a week, maybe we do it twice a week, and people recycle more frequently, right? So we're going to set up this reinforcement learning agent and say, look at all this. We put it into a blender, sort of combine everything together, and then it goes ahead and uses the built-in logic for a reinforcement learner to say, okay, if we look at all these different scenarios and these different actions, what is the most likely action that we would recommend? So it goes ahead and creates a nice matrix when everything is done based on the population density and the waste generated per capita. These are the recommendations that the reinforcement learner came up with. And then this 0, 1, 2, 3, 4, 5, this would be like the neighborhood name or some type of identifier for a neighborhood. So I just map the data. These are actually indices in the data frame, but more than likely we would have either a neighborhood name or maybe a neighborhood broken into a couple different parts, like north, south, east, west Boulder, northeast Boulder, southwest Boulder, something like that. You'd have like different indicators or different identifiers over here. All I have is 0 to 100, so I have 100 rows, so it's not really meaningful identifier, but these are 100 different, we could say, sub-neighborhoods or parts of Boulder, smaller parts of the neighborhood of Boulder, right? So we could say for this part, we would add more bins, add more bins, add more bins. So the reinforcement learner by and far says most of the scenarios that we can help to improve recycling is add more bins. Apparently people are just running out of bins. The bins are overflowing with recycled materials and people have nowhere else to put it. So maybe improved collection frequency if we don't have too many bins, but then we have to drive more trucks. We have to hire more staff. There's more time for people to drive around and collect that. If we put out 2 bins or maybe 3 instead of 1 or maybe 2, whatever it is now, we don't have to have more trucks, right? We don't need increased collection frequency. That is one option, but it's going to be more expensive. Advertising campaign or marketing or awareness, raising people's awareness, that's expensive. We have to buy time on the radio, billboards, TV, flyers, whatever the medium is you choose, right? Just adding more bins is the cheapest, most bang for the buck right here, just by adding more bins. I looked at the unique count of all of these, and where does that come from? Print unique. Oh, value counts. Yeah, value counts. So that was the last time I looked at. By and large, just adding more bins, 97% of the time, 97 out of 100. Remember, this starts with 0, so it goes from 0 to 100. 97 times out of 100, just add more bins, and you're going to get more people recycling. And 2 parts of Boulder and some sections of this neighborhood increase collection frequency. That is recommended action. And awareness campaign, 1 time out of 100, that is the recommended outcome, right? But by and large, just add 2 bins if you have 1, add 3 if you have 2. That's it. You don't have to spend time to advertise and to market awareness, to raise awareness, and you don't have to drive more trucks more frequently, right? That's it. Simple. So that is a win. So the clustering wasn't very successful, but the sorry, I lost my train of thought. But the reinforcement learner was successful, and the optimal vehicle route planning was successful too. So we had a couple successes, a couple kind of hits, definitely a couple of misses, but that's how it goes in the data science world, right? So here's some notes on reinforcement learning. You can look at that. And this was actually pretty interesting when I was putting together this lesson. I learned quite a bit, so I think I might do some more videos on these reinforcement learners. It's kind of an interesting technique in the data science world. I didn't touch on that too much. I think I didn't touch on it much at all. This might be the first. I have to go back and look at all the videos. Now it's getting to be a pretty extensive number. I think this is close to 180 or over 180. But this is a very fascinating topic, so I think I'm going to devote a little more time to that. So that's that. And then what is the last thing? Oh, anomaly detection for waste patterns. Yeah, so one more experiment that I tried is using this isolation forest. This is one way to look for anomalies. There's a bunch of different ways. This is one technique that's very popular, very scalable, upwards and outwards. And a lot of people use this because the outcome is intuitive and it's pretty easy to set up and to run to. So you can see the different features in the data frame. I'm putting that into a new variable called waste features. If I could do Control F, let me see where that goes. Okay, so we're predicting based on these features right here. Okay, You tell me what's an anomaly. So an anomaly is -1 and normal is 1. Okay, so we're looking for anomalies, -1. We assign a 1 if it's not an anomaly. And we have this data frame down here. Anomalies go to this data frame. If equals -1, these are the anomalies right here. And let's see, display anomalies. You know what? If I did this, actually, let me try one more thing here. This might actually crash. Let me see if this crashes. Would it? I think that'll work. Let me try it. Let me try it. Oh, display. Dot head. Let me try this thing. And it's running, and it worked. Okay, so these are the anomalies. This looks at the entire data frame. That's why I wanted to show you this. So the anomalies, again, are -1. So you just see a couple of records over here. But these, all of these are anomalies, right? And if I go one back here without even the head takes the top 5 by default. Let's see how many anomalies. There's only 5. There's only a total of 5 anomalies, right? So 95% of the time, all of these features in data frame are encoded with a non-anomaly encoding feature right here. So this is 1. The anomalies are -1. So we only have 5 out of 100. So only 5% of the time we find anomalies, right? And again, it's based on these features over here. And then we can actually delete that. I don't need that because I have all the anomalies displayed. I didn't know if there's more or less. There's only 5 to begin with. So based on population density, waste generated per capita, and measured in this metric, kilograms per year, industrial activity level, these are the anomalies in the entire population of Boulder. We only have 5 out of 100, right? So pretty small, but that can require some more attention and devotion, right? And we can focus on these. And if we spend a little more time on these items over here, we can try to improve the way that recycling is done for the town of Boulder, right? So I have a couple more things in my notes down here. You can look at that. I'm just about bumping my head on 30 minutes. I just went over 30 minutes here, so I'm going to wrap it up now. One more thing is scatter plot. I'm looking at anomalies right here based on the isolation forest. And I think we see 5, 1, 2, 3, 4, 5, and those are plotted. So we see the anomalies relative to the general non-anomaly population right here. These are blue circles. The anomalies are red triangles, right? Or red squares or rhombuses. I guess you can call them a rhombus maybe. And you can see based on population density and waste generated per capita where the anomalies fall in the whole population. Okay, so hopefully that is somewhat useful. And here we'll have the 5 again, 1, 2, 3, 4, 5, and you can zoom in, zoom out. Again, we're using a 3D graph, just experimenting with it. I don't know if this is tremendously useful. I think the 2D graph might actually be better in this case, but I'll give you that just to play around with. Okay, so that pretty much wraps it up. Hopefully you guys got something useful out of this. Hopefully it was a worthwhile exercise. I learned a little bit when I was putting these scripts together, and hopefully you do too. So I'll share all this code with you guys, and I'll post a video later today. Keep an eye out for that, and I'll see you guys in the next one. Bye for now.